Welcome. Solar cycle 25 is definitely on the rise, and some of the new cycle regions are beginning to last a fairly long time. We've just had such a region cross the disk of the Sun that's lasted basically 2 weeks, and so I'm going to follow the evolution of that region as it decays slowly away, and I've called this video Death of a Sunspot. I'll also give a short update as to the status of solar cycle 25 at the end. I hope you will enjoy. The sunspot region I'm referring to is region 2770, and here is a series of pictures taken each 1 day apart. On the 3rd of August it appeared over the east limb of the Sun. You can just about see it there in the top left image. It took a couple of days before it was fully onto the disk, and then you could see the full extent of the region. It was led by a large single sunspot with a penumbra, that's the grey area around it, and some satellite spots trailing behind. I've put a reference size for the size of the Earth on there, and you can see the sunspot was about the same size as the Earth. So this is sort of an average sunspot. By day 6, that sunspot was starting to break apart. You can see that there's a little bright lane between the two parts of the sunspot there. By day 8, it had actually broken away and become two separate sunspots, and the size of the penumbra had dropped. By day 10, that second spot had disappeared, leaving only a couple of very small satellite spots and the main spot having diminished completely. By day 11 it was almost gone, and it showed a little bit of resurgence today on the 14th, but nonetheless it's still disappearing quite quickly, and maybe the last we see of this sunspot, because as it gets closer to the limb it gets more difficult to see. It probably will not be a returning region next time around. One of the things to notice in the images as it came onto the disk and leaves the disk are these bright areas around the sunspots. These are called faculae, and there's areas of slightly hotter surface of the Sun which emits a little bit more light. These persist long after the sunspot has disappeared, so when this region comes back there's a fair chance there's going to be a little bright patch of faculae where this sunspot used to be. Faculae are very important because they actually add to the amount of energy that comes from the Sun, and so affects the solar cycle. That's why the Sun is brighter at solar maximum, despite the fact of having these dark sunspots on the Sun at that particular time. The number and intensity of the faculae overwhelm the deficit from the sunspot in the long term. Now let's take a look at a movie of the transit of this image across the solar disk over the last 12 days. You'll see it appear over the east limb on the left, transit all the way across the disk to nearly to the west limb, and as it does so you'll see those stages of decay. This is the equivalent set of 12 images covering the transit of this sunspot region, but now seen in magnetic fields. This is so-called magnetogram. The convention here is that light colored magnetic field is coming towards you and dark colored field is going away from you. The fact that you have positive field leading here and negative field trailing means that this is a solar cycle 25 region in the northern hemisphere. We can see that the large spot here is that very intense white blob in the middle of the images, and that slowly decays away as the sunspot transits the disk. The region also becomes more spread out and weaker as it does so, and this is the reason why the sunspots are disappearing. Another interesting factor that you may notice here is that there seems to be these sort of hexagonal boxes in each one of the regions, and several of them in the region. Now these are called supergranular cells, and this is upwelling of hot material from the interior of the Sun in a convection cell. So the hot material is coming up in the middle, moving sideways and then going back down at the edges, and as it does so it carries the magnetic field to the edge of the cell. This also helps to break up the region if their convection is strong. Now let's take a look at that magnetic data as a movie, just like we did before. So this is from the HMI magnetograms. And again, 1 second is approximately equal to 1 day. When a region like this is decaying, you'll often get some small flares out of it. In fact, we even got a C flare out of this region on the 8th of August. But you can see there are lots of little bursts of energy coming out of it. And that's because in the decay process of the magnetic field, you are destroying magnetic field, which produces energy. So you get these little micro flares all the way through the process. We can see these in the high temperature plasma with the data taken by the AIA instrument on SDO. Here we're going to use the 171 angstrom channel, which is approximately equivalent to 650,000 degrees Kelvin, which is the low temperature corona. We should be able to see very clearly the X-ray brightenings in these regions, particularly, and the one we're looking at is the one on the left of these three bright areas on the disk. So that's active region 2770. At one point, we had three news cycle regions on the Sun at the same time. This is the first time it has happened so far this cycle. We have 2770, the one we've been talking about, on the left, 2769 in the middle, and 2768 on the right. Now, each one of these regions is in a different state of decay. 2768 is a very old region and is starting to be pulled apart completely by the differential rotation of the Sun. 2769 is a little bit more compact but weak as well, and neither of these at this time had a sunspot. 2770, with that bright concentrated patch in the lower right, still got a very strong sunspot. But as it goes across, you see it'll start more to resemble 69 and 68. When you think about it, the formation of a sunspot is somewhat of a miracle of it in its own right, because all the forces seem to be trying to pull the thing apart. First of all, sunspots are unipolar magnetic structures, i.e. they're all got the same polarity, and as you know, magnetic fields try to push themselves apart. So sunspots are naturally trying to disperse. The Sun also rotates differentially both in latitude and depth. This picture on the right shows the rotation rate of the Sun. Red here indicates fast rotation of the Sun, blue here indicates slower rotation. At the equator, the Sun is rotating in about every 27 days, and at the pole, at about 34 days with respect to the Earth. So this is sort of winding up the field. But you have a similar phenomena as you go deeper into the Sun. Different parts of the solar interior rotate at different rates. So any coherent structure will be pulled apart, both at the surface and also being attacked from below. And then, of course, there's the convection cells, which help to try to spread out the magnetic field as well. For some obscure reason, people like to count the number of spots on the Sun, or at least the number of spotless days on the Sun, I should say. Last year, that number was running between 80 and 90% of the time had no sunspots on it at all, and that's why I argued that period was probably where solar minimum will turn out being. However, in the last 42 days, only 33% of the days have been spotless, showing that solar cycle 25 is beginning to take hold. In that time, we've had 4 solar cycle 24 regions, all of which were relatively weak and short-lived, and 12 solar cycle 25 regions, many of which were very strong sunspot regions, and in fact some lasting for more than 20 days. This makes me believe that we are on the rise phase to solar cycle 25's maximum in something like 3 to 5 years' time. Here's a plot of the number of spotless days since January of 2016 through to the current time. The blue here indicates the number of spotless days, and the orange here indicates the number of days in that particular month. And as you can see, in the latter half of 2019, there were very, very few sunspots on the Sun at all for nearly 7 months. And that's why I argue that is probably solar minimum. Since then, the number of spotless days has steadily declined, and I suspect August will be even yet lower than July. So far this minimum, we've had 749 spotless days as of August 13th, and that represents only 68% of the time. Here we have a plot of the sunspot number as a function of time, as recorded by the Solar Influence Data Center in Belgium. You can see here solar cycle 24, which was a double peaked cycle, peaking eventually in April of 2014. Since then there was a fairly steep decline into solar minimum, and there is very clearly the time when there was almost no sunspots on the sun for 6 months, and so that's where I think solar minimum is. And since then the number of sunspots has started to pick up, and that's mostly with activity from solar cycle 25. In this first plot on the right, I've smoothed the sunspot data over a period of 12 months. You can see when you do that, the minimum occurs sometime late in 2019. However, the uncertainty on that average is shown by this arrow here. So any time plus or minus 3 months from that time is likely to be the time of solar minimum. You can also see the swap over from solar cycle 24 to solar cycle 25 in the number of sunspot regions of each type. In blue here we have the number of solar cycle 24 regions that appeared in any given month, and that started off high and has been getting steadily lower. And in orange you have the number of solar cycle 25 regions that started off low and has been rising quite rapidly ever since. And of course we're only halfway through August, so that number is likely to grow quite considerably. So I think we're definitely in the rise of solar cycle 25. So exciting times lay ahead. We found that sunspots can last from a few hours to several months, and eventually differential rotation of the sun pulls them apart. Solar minimum happened late last year. Solar cycle 25 is well on its rise phase now towards solar maximum, which will occur in 3 to 5 years' time. The prediction is that the maximum will be larger than solar cycle 24. So until next time, stay safe and goodbye.